Well, hi guys. We're going to have a look at the final section of our binomial distribution study today. And this is a very interesting area where the sample size is unknown and we have to find the sample size. This gets a little bit crazy. So there are some instances where you can do it analytically. There are others where you really just have to use trial and error, and I'll show you an example of both, okay? Now, let's get going and you'll see what I mean as we go along. So basically we've got a question here where we're saying the probability of hitting a bullseye in darts is 0.4, and we're asked what is the least number of games, that is the number of trials, guys, that must be played in order to ensure that the probability of winning at least twice, that's 2 or more, is more than 0.95. So now that means the sample size is unknown. The most difficult, most knotty kind of problem they can throw at you in binomial distributions. So, yes, we have the number of trials is unknown. So let's just try and get our head together. We're saying here the probability, if the probability is greater than or equal to 2 wins, that's what we're saying. We have to have that probability greater than 0.95. Now, I can turn that round the other way for this particular problem into a manageable scenario where I'm saying that the probability of less than 2 wins is less than or equal to 0.05, and that means I've got all bases covered. Less than 2 must be less than or equal to 0.05, and I can work with that. I can work with that without having to use trial and error. That's right. It's easier. Thank you, Mr. Computer. It's easier to work with. So we're going to let the number of trials be n because that's what we don't know, okay? Right. Now we're saying that the probability of x is 0, that's no bullseyes, plus the probability of x is 1, that means 1 bullseye, where capital X means the number of bullseyes, okay? Get that clear into your mind. That is less than 2. That means 0 or 1 means less than 2. Okay, now I'm going to put that in binomial speak, maths speak, and see what we come up with. No wins is NC 0, 0.4 to the 0 times 0.6 to the n. Okay, remember the chance of getting a bullseye is 0.4. So that's that one. Now here comes the next one. NC1 times 0.4 to the 1 times 0.6 to the n minus 1, whatever n is. That's what we're going to find out. Now that has to be less than or equal to 0.05. Do you get that? I think we do. Now let's just simplify that a little bit. NC0, in fact anything C0 is 1. 0.4 to the 0 is 1, and we're just left with 0.6 to the n, plus NC1 will be n, 0.4 to the 1 is 0.4, and then 0.6 to the n minus 1. That has to be less than or equal to 0.05. Now, the thing is we want to solve that, okay? We want to solve that. So what have I done? I've simplified it a little bit more, but the bad news, guys, is that the calculator will not solve that inequation, that less than or equal to 0.05. But what it will solve, let me see, keep you in suspense for a minute, won't solve that. But if you cross that out and make that into an equal sign, now it will solve it. This is just one of the quirks of the operating system of your calculator. It will solve that. So what we do is we solve it for whether it equals 0.05, and we get that. And then we test. Now, look, n can't be minus 1.46. Not on planet Earth it can't. That's the number of trials. That's the number of throws. You can't have a negative number of throws of the dart. Can you? No. Or n is 9.8. 2126. That's the theoretical number of n. So that obviously means you can't have n is 9 point something. You either have 9 throws or you have 10 throws, don't you? So we've got to work out which one is the nearest one which gets us less than or equal to, looks like less than because of the decimal thing, than 0.05, okay? That's what I'm saying. Yeah, that can't be negative, and n has to be a whole number, so it's going to be 9 or 10, and we're going to test both of those to see which one is our winner, okay? I think it's probably going to be 10, but just let's see how it pans out. Yeah, we test both of those, okay? Over the screen we go. Now, there's my solve statement on the calculator for just solving that equation that we had. That inequation of which we've just turned into an equation. And there's the solutions, okay? So we got that one there, that's 9.82, that's jolly good. Now, meanwhile, there is my test. First of all, on the first line there you can see for 9, and I got 0.07, so that's too high for the probability. Then I tested it for 10, and I got 0.046. So you can see 9 is too high, 10 is just below the 0.05, so therefore 10 is the winner. So it has to be 10 trials, okay? Yeah, that's right, 10 trials is our winner. So 10 games needed to get our criterion met, okay? Can you see how to do that? Now, see, that's okay. If they say things like at least 2 bullseyes or stuff like that, we can turn it around to the other side and say, well, we'll go for the one minus the probability they say, which in that case was 0.95, and we'd have just 0 or 1 games. You see, you can handle that. But if you had, say, 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 games, it's doubtful whether the calculator would solve that. So it's only in very limited instances where we can get the calculator to actually solve it. If it won't, you have to use trial and error. Here's a classic example of trial and error. So you've got Gary is kicking the football at football training. He knows from his past experiences that his chance of kicking a goal with any one kick is about 65% or 0.65. His coach has asked him to keep practicing until he scores 50 goals. I'm glad I'm not Gary. How many kicks would he have to attempt in order to ensure that the probability of kicking at least 50 goals is more than 0.99? Look, guys, that is way beyond the realm of what we can do with an analytical, precise equation, okay? Because we're dealing with 50, at least 50 here. Whichever way you cut it, that's too much for the calculator to handle. So we have to use trial and error. The number of trials is unknown. So what we're going to say is let the number of trials be n. Now, the best way to use trial and error is to put I'll show you. We actually use what's called a table of values. It's the most systematic way of checking right down the list for various values of n what the cumulative probability would be. Okay, so I'll show you. Probability of one success is 0.65, and we're going to use trial and error, and we'll use a table of values. Now, what you do is, first of all, on your calculator screen, you type in the binomial cumulative distribution for, and I've used x here instead of n. That'll be equally okay. So I've said binom CDF, that's x trials, comma, 0.65 probability of success, comma, lower bound is 50 trials and upper bound is max possible successes would be x, being our number of trials, okay? I've just plugged that into the calculator and I got that expression over the right hand side just echoed, and then I basically did a cut and paste of the line above on the left hand side, and I made that into f1 of x, into a function, okay? Then once you've done that, you insert a yes, done that. You insert a lists and spreadsheet, okay? You insert a list and spreadsheet. That's Control I does that, okay? And you select lists and spreadsheets for what it is you want to insert, right? Good. Then you convert to a function table via the menu instruction. So you can flip-flop between a lists and spreadsheet and a function table once you're in the lists and spreadsheet application page. Okay. Now, once you're into a function table, via the menu you can select whichever functions are already programmed into your calculator on the calculator screen. And I had made our function f1 of x, so you can select that one. And you can also you can alter the table settings so that you can change what value of x, or I really mean n, if you know what I mean, you start at, and how much you increment by for each successive row on the listing of the function table list out. I'll show you that in a minute. So you could start at 50 and go up by 1, I'd say, for your x, e.g. n. Right, start at 50, step by 1. Yes, I think so. Now I think we're going to go over the screen. Look at that. Very, very nice. So that is the result of what I was just describing to you. I'm now in the lists and spreadsheet application converted to a function table. I've selected f1 of x. And you can see there up at the top left, it's a binomial CDF, exactly the formula I put in on my calculator screen. And down the left-hand side, you can see all those numbers incrementing by 1. That is the number of trials. And if you look to the first instance where you just nudging above the 0.99, you'll see that 92 is just under 0.99 and 93 is just over 0.99. My goodness, there's some lawnmowers coming up here, so get prepared for a noise wipeout, guys. Right on, mowers. Oh, you wouldn't believe this. I thought this would be a quiet place to do this. Stand by. Good heavens, they're like from outer space. So, alright, so that's that now. That gives you, hence we need 93 kicks needed for our situation, okay? And that is, Mr. Box, thank you so much. So can you see, that's the best way to do trial and error, instead of just sitting around just doing random guesses and trying to narrow it down. That's a systematic quote-unquote trial and error method, okay, of doing it. And you want to practice that and get good at it, because function tables are the absolute best thing. Even when you've just got a normal graph function and you just don't know how to get the window settings right, you can do a function table of it and you can just nail it really quickly, so you can go back into the graph screen and get your window settings all sorted out. Anyway, enough of my rambling. Thanks very much. Hope you enjoyed all that, and we'll see you next time. Okay, bye for now.